Session. Okay, the next speaker, Professor Trevor Ireland. He's a professor at the Research School of Earth Sciences at the Australian National University. He's worked extensively on the origin of high-temperature materials in the early solar system through study of meteorites and their inclusions, and he's a member of the JAXA Hayabusa II Joint Science Team and a collaborator on the NASA OSIRIS-REx mission. Please welcome Trevor.
I'm standing in for Hayabusa, who I think was invited but had to pull out.
You came last time to talk about the first Hayabusa.
Yeah, so I'm going to cover some of the first Hayabusa, put it into context and touch on what's new about Hayabusa 2. So Hayabusa 2 is very much like Hayabusa 1, so that this is sort of a double rack, so you don't have to worry too much about whether I'm talking about 1 or 2, except at the end. You'll take note of something which is new. So Hayabusa 1 is a JAXA mission, JAXA Aerospace Exploration Agency, to asteroid 25143 Itokawa, which is a stony asteroid. So you guys talking about mining asteroids, this is what it's all about, getting to an asteroid and bringing something back to Australia, bringing back something to Australia, as it turns out. So the spacecraft is shown down on the bottom right there. It's this square object with wings, and so it looks like a falcon. It's designed to hover, come down, grab a sample, get back up, think about it, maybe go get back down again. So Hayabusa means falcon in Japanese, so it's associated with that. As you can see, it's rather square. It's about the size of a very large refrigerator. And we'll come back to that in a minute. So it was launched in 2003 with the prospect of being the first sample return mission to an asteroid. First use of ion engines to get there, autonomous navigation because you're going around the solar system, you want it to look after itself pretty much. So the rendezvous was in 2005. It was meant to be back by 2007, according to my coffee mug, but had a few issues at the asteroid and was delayed and basically had to do another orbit of the solar system, finally coming back in 2010. So at Itokawa, if you haven't seen these images before, again we get this double-headed sort of arrangement, merging of two objects. So you've heard about spherical planets, then you get into the potato radius, and these are basically down on the peanut radius. So you get these merging of two different objects, and you can actually see a compression ridge which is formed from the low velocity collision. These are this was sort of one of the close-up images. They didn't actually have a close-up camera on the back end of the spacecraft. The best images were taken with a telephoto lens from 200 meters. So it's one of these things. You save weight by throwing away your cameras, and you take an extra 50 kilograms of xenon along just in case you need it. But that's the way it goes. Engineers. Speaking of engineers, so I turned up in Japan for sample selection site. Sound familiar? So we were given the opportunity to choose where we wanted to go on Itokawa, and so there were two prospective sites. We go back quickly. You can see here there's a boulder on the end here that's about 50 meters long. There's some smooth regions and there's sort of rubbly regions. And so as geologists say, gee, wouldn't it be nice to have one smooth region and one rubbly region? And so you go along there and they give you that prospect, and then they say the engineers have said no. You can choose point A. Point A sounds good. So that's what happened. So it descended down to the surface, and this must be a fundamental characteristic of sampling missions because it bounced. It hit the surface early and then came back up and eventually settled down on its side. Sound familiar? So because it had hit early, the gun which is meant to go off, and I'll show you some movies of this later on, the gun didn't fire, the sample didn't come up, so all we got was the accidental entrainment of the dust which was stirred up as it bounced onto the surface. So then there was a second attempt to go down, and so this time safety interlock's been taken off, we know where we are, everything is good. Unfortunately, this is 15 minutes away, and it's light minutes, and everybody's sitting waiting what happened. And no communications back, and then it's like, well, what actually happened? And then some garbled message came back, and then it was cut off. And so the communications were lost. It went into this uncontrolled firing phase, all the chemical thrusters just took off, so it just started chaotically spiraling and spinning, doing the ballerina trick, and there was no confirmed sample in that side either. So, to cut a long story short, here comes the return of the capsule for Hayabusa 1, and remember it looks like a refrigerator. This is the aerodynamics of a refrigerator coming into the surface of or coming up into the upper atmosphere of the Earth. The really neat thing about this was we could immediately see it that the capsule was out in front. Out behind is our refrigerator with the xenon sort of doing its thing and creating an absolutely spectacular show. So they had to do this because it was delayed that long. They weren't sure if the battery was going to last, and so the jettison was last minute as much as possible. And down it came flawlessly. So we got up to Woomera or up to Kubapedi to watch this, and by the time we were coming back, we could see the helicopter zooming around. They'd already found the capsule and taken photographs of it, and the press was going spastic over it. Here's Hajime here, and me and Mike Zelensky looking at the capsule, and Hajime's set up in Woomera, which was a little clean room that had set up to contain the capsule. Lots of really interesting information out of it. Cut a long story short, 1,500 particles were eventually removed out of the capsule. 400 microns max. The gun didn't go off. We actually got the sample of the surface of an asteroid. We didn't get another meteorite. We actually got an asteroid. So making a good story out of things that go wrong is, everybody's expert at that now with space missions. But this really was good because this gave us the very skin of the asteroid. And we could pretty quickly tell that this was a meteorite we'd seen before, and these were chondrites, there's olivine, there's pyroxene, troilite, which is an iron sulfide, and a bit of plagioclase. These are all meteoritic minerals. We knew we had the right stuff. And I think this is the really neat thing about this whole mission was the cosmic ray exposure age, which is given by the neon isotopes. If you expose the surface to cosmic rays, you get the breakdown of the particles into neon isotopes, and it sort of goes from this sort of position from solar wind and starts to spallate down to cosmogenic neon. And the calculations of this basically show that this object can't be any older than 8 million years, and some of the other data we've got suggests it's very much younger. So the whole asteroid has not been there in geological terms for very long at all. So the Hayabusa 1 was a complete success, great public support for Hayabusa in Japan. That turned into support for Hayabusa 2, but then there's only a 3-year window. You've basically got to turn around and put the same mission back together again. The target is now 1993 JU3 Ryugu, which is a C-type asteroid with a prospect of being a carbonaceous type of body, similar to an asteroid or to Ceres, diameter of 900 meters and various things. Destined to left last year, and it's destined to come back 2020. Mission objectives very similar to what happened with Hayabusa 1, touch and go, and the Minerva drop-off cameras. But this is another one, the MASCOT lander the Germans have put together. Only the Germans could do this. A Petrographic Microscope in a drop-off box that you can drop onto the surface, get high magnification images of the mineralogy on the surface and various other things. It was originally designed for Marco Polo. That hasn't been approved. They wanted to get it onto Hayabusa. But this is the intriguing one. Small Carry-on Impactor. A 2.5 kilogram copper impactor will be accelerated to 2 kilometers per second by a 4.5 kilogram shaped charge. Ethics, anyone? So this is going to create a crater with fresh material exposed. Basically, this is creating a new meteorite sample. So to get an internal sample. During this, Hayabusa 2 scuttles around to the other side and sort of ducks around and sort of waits for the all clear. So this is Hayabusa 2 taking off last year.
We had a liftoff of the H3 launch vehicle number 26 with the Hayabusa 2 and 2-second repeat was aboard from the International Space Center at 1:22:04.
So that worked well. So what happens then is this is the Hayabusa One Trajectory. So basically it comes out, goes into Earth orbit, goes away, and comes back. For the sake of time, let's just click through this one. So this is the, actually, yeah, so this is the small chart, the impactor. Basically it jettisons this off, it scuttles around the other side, and basically the kind of gentler sampling of asteroids. You guys might want to think about that for mining. Then you come in, sample in the bottom of the crater, and take away fresh material, maybe with fresh organics, because you're looking at a carbonaceous type chondrite, and so you might find that there's more material underneath. And then return to Woomera in December 2020, hopefully as successfully as Hayabusa 1. So we'll leave it there. So in conclusion, Hayabusa, the mission completed the sample return to the asteroid, and you could argue quite reasonably that it mined a very small amount of sample from the very surface, got the skin of that asteroid that we actually really wanted. It's got all that deformation of the micrometeorite impacts, it's got exposure age, all of that good stuff. It's telling us about an asteroid, it's not telling us about a meteorite. So that was a completely successful mission, and we're very hopeful that Hayabusa 2 is going to be the same. Thank you.
You said, I think, that the asteroid hadn't been around too long. Where might it have come from?
It's a rubble pile. I didn't say that. It's a rubble pile asteroid, and so this could have been disturbed at any stage in the last 8 million years. So there's various things that could be going on. You could have space erosion. You could have erosion. So you're actually losing. It's a rubble pile, so it's just crunching against the individual boulders and re-eroding. It could have been assembled from, self-assembled again from what it was now. It could have been hit, sort of flown apart, reassembled again. Or it could have been out on the asteroid belt, and the collision there has basically sent that into Earth orbit 8 million years ago or something like that. So all various possibilities. It's like totally unexpected, and so
Right.
interesting history.
Mysteries.
The shape charge on the Hayabusa 2, what are the chances of the explosives causing contamination?
Of copper? Very high.
The organic.
The organics?
Yeah.
I don't think this is a good idea. It's it's a
But-
technology demonstration. If they can get onto the surface of the asteroid and get the bullet to fire, get plenty of material, I don't think this is going to generate anything that's going to make it worthwhile.
Yeah.
So the question will be, and this will be the real question, is if they touch down once and the gun works, are they going to risk the mission by trying to drop down again? So they've got the Minerva little throwaway cameras down onto the surface. They've got MASCOT to go down. They'll have all the imaging material from that. That'll be transported back. But then you've got the spacecraft touching down, taking a sample. Do you risk going down again? If it comes back with a confirmed sample with everything else. So that'll be the big question that once it's maybe actually worked. Yep.
What would be the feasibility of, say, putting a seismic receiver on missions while dropping it under the surface and getting seismic measurements and impacts it?
Absolutely zero, because it's not on the mission. In a future mission, yeah, I agree, that would make a lot of sense, especially with something like a rubble pile asteroid, and you're actually firing a shape charge, and for goodness sake, of course you put a seismometer into one of these drop-off cameras, you've got 3 of them, so you can have them deployed in various positions. How does this rubble pile actually react to actually an impact? But this is a C-type asteroid, it could be more massive, a solid body, could still be a rubble pile, you just don't know. But yeah, I agree, it would have been something fairly straightforward to do, is to put a small seismometer into it.
Okay, got the last question up the back.
I'm just wondering, if the point of the technology demonstration, is that geared towards destroying potentially hazardous?
Technology demonstration is a bit of a fallback term if something goes wrong. So it basically says that you thought about it, you thought it was a good idea, but if it fails, it was a technology demonstration. So the original scoring for JAXA was that they would get 100% for the mission if they got there, landed, and everything else like that. But basically, various things got inflated, so it's now a 1,000% successful mission. So it's one of these things. It is technology that hasn't been used before, and so then it becomes a technology demonstration.
What's the actual point of it?
Look, personally, I really don't think it's going to be it's a good thing to do. I just don't see the value of getting something which is basically another sample of a meteorite. But potentially it may be a parent body that we've never seen before, and so we could, having fresh material below the skin, below a lot of the space weathering, having that could be useful to actually compare what we get from the actual skin of the asteroid with what's actually on the interior. So there are some good things about it, but it's like the trade-off will come when we decide if we've got a sample, do we risk going through this procedure? As Jonathan said, it's potentially going to have, I don't know what the organics will be, but you're right, they will be a possibility of contamination from those alone.
Okay, thanks Trevor. If anyone wants any more questions, we can wait till the end.